name of this course is process control and instrumentation. Initially, we will cover the process control and then the instrumentation course. So, the first topic is introduction to process control. Introduction to process control. This topic we will cover first. Now, in chemical engineering, we have a number of chemical units. For example, reactors. For example, distillation column, like pump, compressor, etc. These are the different units which are extensively used in chemical engineering. Now, to constitute a chemical plant, we need to assemble few of these units. Fine. If we assemble few of these units, then we can constitute a chemical plant. Now, what is the objective of a chemical plant? What is the objective of a chemical plant? Suppose we have a plant. Now, it receives raw material. So, input to this plant is raw material and output is product. So, basically the plant receives raw material using different available sources of energy. The plant produces products in the most economical way. This is the objective of a plant. Fine. It receives raw material, it uses available sources of energy, then it produces product in the most economical way. This is the objective. Now, to meet these objectives, we need to satisfy some requirements. To meet these objective, we need to meet some requirements. What are these requirements? The primary requirement is safety. The primary requirement is safety. Say for example, a reactor which is designed to operate within 100 psi pressure. Fine. We have one reactor which is designed to operate within 100 psi pressure. Now, to maintain this pressure, we need some external intervention so that the reactor operates below this limit. This is the first requirement, that is safety. Second one is the production specifications. Production specification. A process must produce desired amounts of product and desired quality of product. So, first one is quality and second one is quantity. This is the product specifications. We need to maintain the quantity as well as the quality. That is the product specification. Third important point is environmental requirements. Environmental requirements. So, there are a number of state and federal laws. There are a number of state and federal laws which enforce to maintain, say for example, the concentration of chemicals. Say for example, it is required to maintain the concentration of chemicals in the effluent stream. Now, another example is sulfur dioxide concentration in the stream which is rejected to the atmosphere. Second environmental requirement is to maintain the sulfur dioxide concentration, this is example, which is rejected to the atmosphere. And third example is the wastewater which is returned to the river or lake. These are three examples under the environmental regulations. Fine. Next important requirement is operational constraints. Operational constraints. Now, the plant have certain constraints inherent to the operation. The plants have certain constraints inherent to the operation. Say for example, the distillation column, this is the first example, the distillation column should not be flooded. This is one operational constraint. The distillation column should not be flooded. Second example is tanks should not overflow or go dry. Second example is the tanks should not overflow or go dry. Third example is the temperature in a catalytic reactor should not exceed the upper limit. If we consider a catalytic reactor, so the temperature should not exceed the upper limit, because if the temperature is higher than the upper limit, the catalyst may be destroyed. Fine. So, this is all about the operational constraints. Fifth one is the economics. Economics. So, it is required to control the operating conditions at given optimum level of minimum operating cost, maximum profit, etc. Say for example, we need to judiciously use the raw materials, the energy used in the process, the human labor, so that we can minimize the operating cost and maximize the profit. Fine. So, these are all about the requirements to meet the plant objective. Now, it is very obvious from this discussion that to maintain all these requirements, there is some external intervention is required. Fine. And that external intervention is nothing but the control system. Fine. So, to maintain, to meet all these requirements, we need to devise a control system. Next, we will discuss three important issues. Three important issues which can be dealt by the control system. What are these issues? First issue is the influence of external disturbances. This is the first issue, the influence of external disturbances. Second one is the stability of a chemical process. This is the second issue, and third one is the performance of a chemical process. The performance of a chemical process. So, these are the three important issues which should be dealt by the control system. Now, the basic aim of a controller is to suppress the influence of external disturbances. Second one is to ensure the stability of a chemical process, and third one is to optimize the performance of a chemical process. Fine. So, we need to devise a control system which suppress the influence of external disturbances. It ensures the stability of a chemical process and it can optimize the performance of a chemical process. We will discuss all these three issues in brief with the help of control system. So, first we will discuss the external disturbance. External disturbance. So, to discuss this external disturbance, we will consider a simple example, that is a tank heating system. The schematic of the tank heating system is something like this. This is a tank, a liquid stream which is entering this tank with a flow rate of F suffix I. Temperature of this inlet stream is T suffix I. Now, this liquid is oil stirred. The outlet steam flow rate is F and temperature is T. Now, the liquid in this tank has the height of H. Definitely the temperature is also T, because we are considering stirrer. Now, to heat up this process, we need to introduce one coil through which steam is going with a flow rate of F suffix St. Fine. So, this is a heating tank system. A liquid is entering the process with flow rate Fi and temperature Ti. The outlet flow has the rate of F and temperature T. One coil is introduced for heating the liquid, and through the coil steam is passing with a flow rate of F St. Now, what is the objective of this process? That we need to mention first. What is the objective of this process? First objective is to maintain the liquid temperature T at its desired value. That desired value is, suppose, T suffix D. This is the first objective. The temperature of the liquid should be maintained at its desired temperature, that is T D. Similarly, the second objective of this process is we need to maintain the height of liquid in the tank at its desired value, that is H suffix D. Fine. So, these are the two objectives. Now, initially, what are the steps we need to follow for any chemical process? First is we have to follow the startup procedure of a process. Fine. After starting off the process, it reaches at steady state. We are representing that by SS. So, after starting up the process, it reaches at steady state. Now, suppose the process is at steady state, and if there is no external intervention, I mean if there is no change of Fi, there is no change of Ti, there is no change of Fst, the process remains at steady state all the times. Fine. So, if there is no change of any input variables, then the process remains at steady state. So, there is no need of any control system, but this is not the case in practice. Usually, the input variables may change with time, not regularly, but maybe in some interval. Say for example, this feed inlet flow rate which is coming from one upstream unit. So, we do not have any control on Fi and Ti exactly. So, this is the practical case where the input variables may change with time, and that is why we need to devise a control system. Now, question is how we can devise that control system and how we can keep these objectives. Say for example, we are considering the first objective, I mean we need to maintain the temperature at its desired value. How we can maintain that? First of all, we have to measure this temperature of this liquid steam. We can measure the temperature using one thermocouple. So, this is a thermocouple employing which we can measure the temperature of this liquid. And suppose the thermocouple outlet, I mean the temperature which is measured by that thermocouple, that is exactly the liquid temperature T. Now, this temperature is then compared with the desired value, that is T d. Fine. This input T d is given by the person who is in charge of operation, or you can say the value of this T d is specified by the control engineer. Now, we compare this T d and T, and the outlet of this comparator is E, that is nothing but the error, and that error is T d minus T. So, we can do one thing, we can put here positive sign and here negative sign. This error signal goes to a controller. This error signal is the input to the controller. Then this controller produces or calculates control actions, and that control action is implemented through this control valve. Fine. So, this is a heating tank system. We are considering only the first objective, that is we need to maintain the temperature at its desired value. We are not considering the second case. So, initially we need to measure the liquid temperature using one temperature sensor, that is thermocouple. We have assumed that the thermocouple outlet temperature is exactly equal to the liquid tank temperature. Then this temperature is compared with the desired temperature, that is T d. So, we have used one variable, that is error, which is represented by E. E equals to T d minus T. Then this error signal goes to the controller. Controller calculates, and that calculated action is implemented through this valve. Fine. Now, suppose error is greater than 0. This is the first case. Error is greater than 0. It means T d is greater than T. That means the desired temperature is higher than the temperature exists in the liquid system. So, what is required to do for the controller? Yes, the controller will increase the FST. So, it is required to increase the steam flow rate, that means more steam is required to flow through the control valve. This is one case. Similarly, if error is less than 0, in that case the situation is just opposite. I mean TD is less than T, that means the control should reduce the steam flow rate. Control should reduce the steam flow rate. Now, we have to introduce this fact in terms of the disturbance. Here the disturbance is basically the feed flow rate and temperature. Suppose feed flow rate has been increased, this Fi feed flow rate increases. Now, there is no change of the inlet steam flow rate, only change is in Fi. If Fi increases and Fst remains same, then what happens? Temperature increases or decreases? Temperature decreases. So, in this situation, what the controller will do? The controller will increase the steam flow rate. That means, the controller will increase this Fst. So, this is the description in terms of external disturbance. So, it is very clear from this discussion that the controller which suppress the effect of external disturbance. Fine. Next, we will discuss the stability of a chemical process. Secondly, we will discuss the stability of a chemical process. So, we will first draw a plot, we will make a plot, this is x and this is time t. This x may be temperature, x may be concentration, fine. Now, as I mentioned that initially the process is at steady state. Now, at time t equals to t naught, the x is disturbed. This is the steady state value of x. Now, first x is disturbed at t equals to t naught, fine. Now, as a result, the x shows this type of response. That means, x returns automatically to the steady state. X returns automatically to the steady state. If this is the case, this type of process is called stable or self-regulating process. Fine. X returns automatically to the steady state value, and this type of process is called stable process or self-regulating process. So, for this case there is no need of any external intervention, no need of any external intervention. I mean no need of any controller for this stable system. We will consider another case which is unstable. So, this is x versus time, that is t. Initially the process is at steady state, and at time t equals to 0, x is disturbed. X is disturbed at time t equals to t naught. Now, in this case, the response is like this. So, this figure indicates that x does not return to the steady state. Fine. This figure clearly indicates that x does not return to the steady state, and this type of processes are called unstable process. This type of processes are called unstable process, and for this process there is a need of external intervention. There is a need of external intervention. I mean, there is a need of controller. Fine. Now, from this discussion we cannot conclude that for this stable process there is no need of controller. We cannot conclude that, because we have mentioned 3 important issues. So, this is only one issue. For other 2 issues like the suppression of external disturbance, and third one is the optimum performance of the process, for those 2 issues we may need the controller. Not only that, even for this stable process to reach at steady state with a short period of time, we may need a controller. Fine. So, we can say that here also the need of controller we realize. Fine. Next issue is the performance of a chemical process or optimize the performance. Optimize the performance of a process. This is the third issue. Now, the main operational objectives are, first one is the safety, and second objective is production specifications. This is the second objective. Once these are achieved, once these 2 objectives are achieved, the next goal is to make the operation more profitable. Fine. If these 2 objectives are achieved, the next goal is to make the operation more profitable. Now, in that direction we will consider one example, that is a continuous stirred tank reactor. Suppose this is a jacketed reactor. This is a jacketed reactor. This is the schematic of the reactor. Reactant enters the process. This is the reactant and this is the product. Now, in this process, 2 consecutive reactions A to B and then B to C occur. This is two consecutive exothermic reaction occur. A is the reactant, B is the desired product, and C is the undesired product. So, this is basically products. A is the reactant, B is the desired product, and C is the undesired product. Now, what is the economic objective? The economic objective for this process is to maximize the profit, to maximize the profit. Fine. Now, suppose the profit function is phi, and this is integration of 0 to t. T is nothing but the operational time, and here one function will be there. This function is the in terms of revenue from the sales of product B, revenue from the sales of product B, then it includes the cost of reactant A, and then the cost of coolant. Basically, if this is the exothermic reaction, we need to introduce here coolant to take out the exothermic heat, and this is coolant in, this is coolant out. Fine. So, the profit function which includes the revenue from the sales of product B, cost of reactant A, and the cost of coolant. Then we need to maximize the profit. Fine. And then we can maximize the performance, we can say. So, these are all about the three issues which can be dealt by the control system. Next, we will discuss the classification of variables. The variables which are extensively used in process control course, that we will discuss in the next. So, next topic is classification of variables. The variables is usually two types. One is input variable and second one is output variable. Second one is output variable. Now, input variable is again two types. Input variable is again two types. One is the disturbance or load variable. First one is disturbance or load variable, and it is conventionally represented by LV. Second input variable is manipulated or adjustable variable, or sometimes it is called control variable. So, input variable is two types, one is disturbance or load variable and second one is manipulated variable or control variable. This we can represent by MV. Similarly, the output variable, again two types, one is measured output and second one is unmeasured output. So, output variable is two types, again one is measured output and second one is unmeasured output. Another variable is also used, that is controlled variable. So, do not confuse with this control variable. Control variable is manipulated variable and controlled variable we will discuss that, but at this point I can say that the control variables are usually the measured output. Sometimes this is also unmeasured output, fine. So, this is the control variable. So, these are all about the variables. Now, we will take different examples and we will select the different variables for that specific example. So, we will start with a simple liquid tank system. We will first start with a liquid tank, fine. So, this is a liquid tank system. The input to this process is, the input stream has the flow rate of Fi, outlet flow rate is suppose F naught. The liquid in this tank has the height of h and the cross sectional area of this tank is A, fine. Now, this is a simple liquid tank system. So, what is the objective of this process? The objective of this process is to maintain the liquid height in the tank at its desired value Hd, fine. This is the objective of this tank system. Now, here the control variable is height. The control variable we will represent by Cv. The control variable Cv here is liquid height, fine. Now, if we consider this process, so can you classify the variables? So, which one is the input variable for this process? Fi. Input variable is Fi. What are the output variables? One is F and another one is liquid height, fine. The output variables are, one is outlet flow rate F and second one is liquid height. Now, for this example system, can you make a pair in between controlled variable and manipulated variable? We have decided that for this particular system, liquid height in the tank H is the control variable. So, what will be the corresponding manipulated variable? I mean, to maintain this liquid height, which variable we can adjust? F I or F O? I think both we can do, F I and F naught. F I and F naught. I am just making one control configuration. Suppose this F naught is the manipulated variable corresponding to liquid height H. So, what will be the control configuration as we have drawn for the heating tank system. So, first of all we need to measure this height by level sensor. So, here a level sensor we can place which can measure the liquid height. Suppose this is height, then it is compared with the desired value H d. This carries positive sign and this is negative sign. Now, the output of this comparator is error. Error is basically desired height minus height. Then this error signal goes to controller and this control action is implemented here. This is a control valve, fine. So, F naught is the manipulated variable in this control configuration. Now, can you tell me F naught is input variable or output variable? You see the classification, manipulated variable is under input variable or output variable? Input variable. So, if we consider F naught as the manipulated variable, then F naught is input variable, fine. In this example, it is clear that if F naught is manipulated variable, then that is input variable, not output variable, because manipulated variable is one type of input variable. That is why you write within bracket F naught. But if we consider F I is the manipulated variable, in that case F naught is output variable. Clear? Fine. Next, we will take another example to know about all these variables. That example we have considered heating tank system. So, this is a heating tank system. The inlet steam has flow rate F I, temperature T I, and it has the outlet flow rate of F and T. Steam is introduced through this coil. It has the flow rate of F S T and liquid height is here H, temperature T, fine. So, this is the heating tank system, heating tank. Now, what are the inputs in this case? F I, F S T, T I, these are the inputs. And what about F? Maybe input. And what about the outputs? F, T and H. We have mentioned the objective of this process. First objective is to maintain T at its desired value, and second is we need to maintain height at its desired temperature. Can you classify the, can you make the control pairs, I mean manipulated variable and corresponding control variable pairs? So, control variable, one control variable is temperature, because that is our objective. Second control variable is height. How we can maintain this temperature? By adjusting FST, fine. And for the case of height, How we can maintain the height? By adjusting Fi and F naught, Fi and F. Fine. If F is the manipulated variable, as we discussed for the previous example, then F will be one input variable. If Fi is the manipulated variable, in that case F will be output variable. So, Fi and Fst, these two are, suppose for this case, manipulated variable, and this T and height, these two are control variable. So, which one is disturbance variable or load variable? Input variables are two types, one is manipulated variable, another one is load variable. Fi and Fst, they are manipulated variable. So, rest is Ti, so this is load variable. Fine. So, these are all about the variables, different variables. The next we will discuss the control configurations. Although we did not discuss the control configurations in details, but before that we want to know the different configurations. Control configurations. We will consider the distillation example, which is quite complex compared to this liquid tank and heating tank system. Now, first we will consider one control scheme, that is the feedback control scheme. Feedback control. So, distillation column, this is the tower of a distillation column. Feed is introduced here with flow rate F and composition Z. The overhead vapor which leaves the top tray is condensed in this condenser. This is a condenser. Then the condensed liquid is accumulated in a drum, which is the reflux drum. This is also called reflux accumulator. A part of this liquid is recycled back to the top section of the column, and a part is withdrawn as distillate with flow rate D and composition XD. Composition means here mole fraction. Similarly, at the bottom the liquid is withdrawn and it is subjected to a reboiler. The produced vapor is recycled back to the bottom tray and some amount of liquid is taken out as bottoms with flow rate B and composition XB. Fine. So, feed is introduced with flow rate F, composition Z. This is a feed tray, this is the top tray, this is the bottom tray. Now, the overhead vapor goes to a condenser, condensation occurs Then the condensed liquid is accumulated in this reflux drum, and part of this liquid is recycled to the top tray as reflux. This is called reflux rate, a reflux flow, reflux stream, and another part, a part of this accumulated liquid is withdrawn as distillate with flow rate D and composition, or you can say mole fraction x d. Similarly, at the bottom, this liquid which is coming from the bottom tray, it goes to a reboiler. The produced vapor is recycled back just below the bottom tray. This is bottom tray, and some amount of liquid is withdrawn as bottom product or bottoms with flow rate B and composition x b. First, we have to know what is the control objective of this process. There are basically two products, one is distillate, another one is bottoms. We will consider presently the top product. Fine. So, what is the objective? Objective is to maintain the top product composition at its desired value. Fine. This is the objective. If we consider the top section only, we need to maintain the top product composition x d at its desired value. So, what will be the control configuration for this case? If this is our control objective, that means this is the control variable. So, control variable manipulated variable pair we have to make. If x d is the control variable, then corresponding manipulated variable is reflux flow rate R. Fine. Can you make the control configuration now? Yes, we can make it. Suppose here the liquid has composition of x d. So, we need one composition analyzer. We need one composition analyzer to measure x d. Then this analyzer gives the value of x d. Fine. Then that x d is compared in this comparator. This is negative and this is x d, this is x capital D desired, this is positive. Then we get the error signal. This error signal goes to the composition controller, then the control action is implemented through this valve. So, this is the control configuration. So, this is basically the feedback control scheme. In the feedback control scheme, the control variable is measured. Fine. In the feedback control scheme, the controlled variable is measured. Anyway, today we do not have time. So, in the next class we will discuss other two control schemes. They are feed forward control scheme and inferential control scheme along with other topics.